Hello again. Time for another calculus video and probably another terrible joke. Let's be honest, you're getting both. So today's lesson is about the chain rule. And a lot of people think the chain rule only has to do with exponents. It doesn't. So we're going to take the chain rule idea and really make sure you understand all of the pieces. So the chain rule is really about how do you take the derivative of composite functions where there's like one thing happening within another thing. So the first definition I'm going to explain to you of the chain rule is it says if y equals f of u is a differentiable function of u and u equals g of x, that really means that we are taking the derivative of y equals f of g of x, like an embedded composite function there. So the chain rule says if you want to find dy dx, you really find dy du and then multiply it by du dx. In other words, take the derivative of u, which is like your inside function, and take the derivative of your outside function and multiply them together. I think it makes a lot more sense when we look at it in function notation down here. If you have the derivative of f of g of x, then it's f prime of g of x times g prime of x. So a lot of times what you'll hear me say is you take the derivative of the outside, keep the inside, times the derivative of the outside. So derivative of the outside, keep the inside, times the derivative of the inside. All right, so let me give you a couple examples of things that technically don't need the chain rule, and then one that does need the chain rule, and I want to show you that we end up in the same place. So first, we are going to do this with exponents. So it says find f prime first without the chain rule, then find the derivative with the chain rule. So if I look at 4 over x plus 1, if I didn't have the chain rule to use, I would see this as a quotient, and I would do the quotient rule. So f prime of x would be low d high minus high d low all over low times low. So my derivative is really going to be negative 4 over x plus 1 squared. Okay, I'm fine with that. But now it says I can do it with the chain rule as well. So if I want to do this with the chain rule, I need to be able to identify like an outside and an inside. So I'm going to rewrite f of x as 4 times x plus 1 to the negative 1. So my outside function is 4u to the negative 1. Okay, you don't have to write this. Honestly, I'm going to write it in yellow because I really don't want you to write this. But if I had to identify like an outside function, it would be 4u to the negative 1, where u is x plus 1. But really, the way I'm going to talk about it and the way I'm going to think about it is that my outside function is to the negative 1, and my inside function is x plus 1. So let me show you what I mean here. If I want to take the derivative, I'm going to take the derivative of the outside. Well, when I take the derivative of something raised to the negative 1, I'm going to use the power rule. So I'm going to bring down the power and reduce it by 1. Now I need to multiply by the derivative of the inside. The inside is x plus 1. The derivative of that is 1. So bring down the power, reduce it by 1, multiply by the derivative of the inside. Ends me at f prime of x is negative 4 over x plus 1 squared, which is exactly what we had up here. Okay? All right, let's look at part B here. Same idea, different exponent, all right? So same idea, different exponent. Let me change colors here so they don't overlap. So if I want to do part B without the chain rule, if I didn't know that the chain rule existed, I wouldn't be able to take the derivative yet. So I would need to rewrite f of x as 3 times x minus 1 times itself, which is really 3 times x squared minus 2x plus 1, which if you want to distribute the 3x squared minus 6x plus 3. So if I take the derivative of that, I have 6x minus 6. That was a lot of work, though. The chain rule, one of the reasons we have it, is it reduces the amount of work that we got to do. So if I want to take the derivative of this original setup using the chain rule, okay, I'm going to take the derivative of the outside, which means use the product rule. So bring down the 2, reduce it by 1, and then multiply by the derivative of the inside. Well, the derivative of x minus 1 is 1. So f prime of x is 6x minus 6, which is exactly what we had before. Now, those are good examples of when the chain rule is possible, but not necessary. Now let's talk about where we have to use the chain rule. Part C, f of x equals sine 2x. I don't have a power rule. That stinks. So let's talk about the chain rule here. And I'm going to break my own rule. I'm going to do the chain rule first, and then I'm going to not do the chain rule second. So if I start here on part C and I want to do the chain rule, what's my outside? Well, my outside this time is the sine function. The derivative of sine is going to be cosine. There's the derivative of the outside. Keep the inside times the derivative of the inside, and the derivative of 2x is 2. So the derivative of sine 2x is 2 cosine 2x. This can be done without the chain rule if you remember your double angle identities. Mrs. Faber, I don't remember those. That's okay. I'm going to give you a sheet. Don't worry. So this original can be written as f of x equals sine 2x. That's the same as 2 sine x cosine x. That's a double angle identity. So now if I want to take the derivative, I can use the product rule. The first times the derivative of the second plus the second times the derivative of the first. The derivative of 2 sine x is going to be 2 cosine x. So then I get f prime of x is negative 2 sine squared x plus 2 cosine squared x. And there's another identity in here. If I pull this negative 2 out, I am going to have sine squared x minus cosine squared x. That's the double angle identity for cos 2x. Technically, it's negative cos 2x, the way I have it written, which is going to give me positive 2 cosine 2x, which is what I had before. So the nice thing here is, if I use the double angle identity, I've made more work for myself. So let's not do that, and let's just do the chain rule right off the bat. But that last example is a perfect example of the chain rule isn't just for exponents. All right, it's for trig, it's for logarithms, it's for all kinds of things. So let's move on here. And what I'm going to do is I'm going to do a couple of these. Then I'm going to pause the video, do the rest, and then you can scrub through the video and see how I do the rest of them, okay? So on this next page, we're just going to take a bunch of derivatives using the chain rule and any other pertinent rules. So part A here, I have k of x equals x squared plus 1 times the square root of 2x minus 3. If I want to take this derivative, I know I need the product rule, okay? But I also need the chain rule because I have this square root thing, and there's no way I'm getting rid of that. So if I want to take the derivative, if I want to find k prime of x, I'm going to do the product rule. So I'm going to do the first times the derivative of the second. Well, the square root of 2x minus 3 is really 2x minus 3 to the 1/2. So when I take the derivative of that, the chain rule is bring down the power, keep the inside, and reduce the power by 1, and then multiply by the derivative of the inside. Derivative of the outside, keep the inside, times the derivative of the inside. So now I have the first times the derivative of the second plus the second times the derivative of the first. The derivative of x squared plus 1 is 2x. And I mean, I'm going to simplify it just to make it look a little bit nicer. Technically, you could walk away here, but I mean, this is begging for those to disappear. And then maybe I do want to write this as x squared plus 1 over the square root of 2x minus 3 plus 2x root 2x minus 3. And again, I think that looks better. I don't know if it's any easier, but it looks better. So there's my derivative for k. All right, now let's do part B here. Part B, I have g of t equals t minus 1 over 2t plus 5, all raised to the ninth. So if I want to take the derivative of this one, I have a quotient, but that quotient is raised to a power. So my derivative, g prime of t, I wrote x, but I meant t, g prime of t, is going to be bring down the power, reduce it by 1, multiply by the derivative of the inside. So bring down the power, reduce it by 1, but keep everything else the same, and then multiply by the derivative of the inside, which is going to be a quotient rule. So I'm going to have low d high minus high d low all over low times low. And again, I could leave this, but I really want to, I think, at least minimize that last part. So g prime of t is going to be 9, p minus 1, 2t plus 5 to the 8th. And then over here, I have 2t minus 2t, so those are gone. 5 minus negative 2, so that's going to be 7 over 2t plus 5 squared. And honestly, I can multiply that 9 and 7, so that's going to be 63. And then I'm really going to have t minus 1 to the 8th and 2t plus 5 to the 10th. That's another way to write that. Okay. Do you have to know where to keep going and where to stop? No. But do you have to understand the things that I just did are equivalent? Yeah. All right, so there are my derivatives. Cool, cool, cool. All right, I am going to come down here and I am going to do part C and I'm going to do part F and I am going to cross off H because honestly, I don't really like that question. I don't want to do it. So you can ignore that one. So I'm going to do C and F, and then I'm going to get you started on the other couple, and then you're going to do them, pause the video, and then come back. All right, so let's start with C. H of x equals tan sine x. Well, this isn't tan x times sine x. It's the tangent of sine x. So my outside function is the tangent function, and my inside function is the sine function. So if I want to take the derivative, h prime of x, I'm going to take the derivative of the outside. The derivative of tan is secant squared. Derivative of the outside, keep the inside. So it's secant squared of sine x times the derivative of the inside. The derivative of sine x is cosine x. And that is it. That's your derivative. There's nothing else we can do with that, or in other words, really nothing else I want to do with that, and leave it there. Okay. When you start part D, you're going to do that one on your own later. There's not much I can tell you about that one. I want you to think it through. When you think of part E, I know it's written in R and theta, but really all you're going to do is you're going to find dr d theta. And if that freaks you out, rewrite this as y equals sine squared x. Okay. And if you want to take the derivative of that, I highly encourage you to rewrite that as the sine of x squared. Okay, again, I'm not doing that. I'm just getting you set up. Now let's come over to f, which I am going to do. So if I want to find the derivative of 3 tan squared 5x, I'm going to do just like what I said. I'm going to rewrite this as 3 times the tan of 5x squared. And the reason I'm going to do that is because with the squared in the middle, it's really hard to identify what the outside and the inside is. Now, if I write the squared like that, it's very obvious that the outside function is the squared function. So if I want to find m prime of x, I'm going to take the derivative of the outside, which means the power rule. So I'm going to bring down the 2, keep the inside the same, and reduce it by 1. So there's the derivative of the outside, keep the inside. Now I want to do times the derivative of the inside. I have a double chain rule because the derivative of tan 5x, tangent is the outside and 5x is the inside. So when I take the derivative of tan 5x, it's going to be derivative of the outside, derivative of tan, which is secant squared, keep the inside, times the derivative of the inside, which is 5. So when you have trig raised to a power, technically it's always a double chain rule because you have the derivative of the exponent, like the power rule, the derivative of the trig function, and the derivative of your angle piece. And so when I kind of condense this as best I can, that's going to be 30 tan 5x secant squared 5x. Okay. And then I want you to do G on your own. All right. So pause this video, try to do D, E, and G, and then unpause the video and I will go through it. Okay. I am going to go through each question. If you don't feel like you need to see me go through it, just scrub through the video and see if you got it right. I'm cool with that. You can learn how to make these videos efficient for you time-wise and learning-wise. So if you went somewhere, now you're back. I have y equals cosine the square root of x. I'm going to rewrite this as cosine x to the 1/2. And then I'm going to take the derivative. So the derivative of y, the notation I'm going to use is dy dx. Then I'm going to do the derivative of the outside. The derivative of cosine is negative sine. Keep the inside times the derivative of the inside. X to the 1/2 would be a power rule. Bring down the power, reduce it by 1. So if I want to condense this a little bit to make it look nicer, that's a negative 1/2 sine root x. And then really it's divided by root x, which is kind of negative sine root x all over 2 root x. Whatever of those you're comfortable with is fine with me. Okay, so there's a couple derivatives. If I come down here to E is sine squared x, which is really the sine of x squared, or the way I've written it, sine squared theta. So dr d theta is going to be, let's see, derivative of the outside, bring down the power, reduce it by 1, times the derivative of the inside. The derivative of sine is cosine, keep the theta. And then technically, I'm also multiplying by the derivative of theta, which is 1. So the derivative of sine squared theta is dr d theta equals 2 sine theta cos theta, which if you remember from the front, if you wanted to, you could rewrite as sine 2 theta. You do not have to, but you could. All right, and last but not least, we've got G, which is going to be a product rule with a chain rule, because I'm going to rewrite this as 4x times cotan x to the 1/2. I'm bored with that color. Let's change to orange. So the derivative of 4x cotan x raised to the 1/2 is going to be dy dx equals the first times the derivative of the second. Here's the chain rule. Bring down the power, reduce it by 1, multiply by the derivative of the inside. The derivative of cotan is negative cosecant squared, and the derivative of x is 1. So there's bring down the power, reduce it by 1, multiply by the derivative of the inside. I'm only partway done. This is a product rule, so there's the first times the derivative of the second plus the second times the derivative of the first. 4. Whew, that one's ugly. I still want to condense it a little bit, though, just, because I want to. So if I wanted to condense this 1/2 and that 4 could make a 2. I would have a negative. So this is going to be negative x cosecant squared x divided by the square root of cotan x. And then this would be 4 root cotan x. There are many different ways to write it. That's just the way I chose. Okie dokie. So there is the chain rule, part 1. When we get into part 2, I'm going to talk about the chain rule in function notation. So for part 1, you get just a god-awful joke. What do skeletons use to listen to music? What do skeletons use to listen to their music? Scare pods. I made that one up this morning, and maybe it's so bad because I didn't go to sleep last night until after 1 o'clock in the morning. So there's your crappy joke for the day. Maybe not for the day, but at least for this video. And I will be back with part 2 in a little bit. Bye.